Hello and welcome, ladies and gentlemen. My name is Philipp Köppe, and today I have the pleasure to moderate this webinar. The topic of today's webinar is thermokinetics, advantages and disadvantages of different approaches, unique and powerful features of NETZSCH-Gerätebau Neo Software. And your presenter today will be Dr. Elena Moukhina. She has a PhD in physics and has been working at NETZSCH for 20 years now in the software development in the field of thermal analytical data. And I will hand over to her in a minute. Before that, I just wanted to point out two things to you. If you have any questions, you can ask them at any time via the question function of GoToWebinar. And we will try to answer as many as possible at the end of the webinar. For questions that we don't have time to answer, we will respond to you in the coming days via email. And the other point I wanted to mention is that the webinar will be recorded and you will receive the recording in the next few days. But now I don't want to keep you in suspense any longer, and I will hand over to Dr. Moukhina. This will take maybe some seconds.
So, hi everybody. I think you see my screen. It should be green with NETZSCH logo and with our title, Advantages and Disadvantages of Different Thermokinetic Approaches and Unique Features for Kinetics Neo Software. There will be 3 points in our agenda. First, what is the target of thermokinetic analysis? What problems should be solved? A second one, how to solve these problems. What approaches exist and what are advantages and disadvantages of these approaches? And the third one is unique features of Kinetics Neo software. And a special of them is occurring features, really very, very powerful features and unique features with Kamal-Surur, diffusion control, and kinetic analysis of areometry, crystallization, kinetic, and all other features. And now, why we need it? What kind of problems could be solved by this software or by these methods? Firstly, if you speak about electrical insulation, then this electrical insulation has some lifetime. And if it works during some years, maybe then it will be degraded and will be not elastic anymore. And if it is broken, you can imagine what happens if electrical insulation is broken. Then it could be very, very dangerous. And the question is, what is the lifetime for electrical insulation or coating for different temperature, maybe on enhanced temperature inside engines? We should know this. A second question is about recycling. What happens with plastics or with another materials during recycling or pyrolysis? If we speak about some materials which are dangerous or high energetic, for example, explosives, then it's very important to know how stable is this material, at which temperature could be stored and transported, and what is the time what is the safe time for each temperature. Here it is really very important. A second group of the question is connected with chemical reactions like curing and cross-linking. The question is when the paint will be cured, what happens during curing, how high is the reactivity, and what is the final state after curing. Is it liquid, or is it elastic, or is it in glass state? In this case, we sometimes cannot measure, but we can make a simulation and make predictions. And now is the question how to do these predictions. The last big group of problems are the industrial problems. For example, ceramic, the production of ceramics. During sintering, you know that the quality of ceramics depends on the firing and firing temperature and time. And if it's too long, then we lose the time and it is really very expensive. If it's too short and very, very fast heating, then we lose the quality. We have some cracks, we have some deformation, and it is also not good. Sometimes it's necessary to find what is the optimal temperature profile for industrial process. And it's a really big problem because usually it is solved by try and error during several months. And with the software, it could be done with one click. What is the common for all these questions? Here we have some process, usually it's chemical process, with some reactant and product. The first question, what happens during this chemical process? Are there some intermediate steps? Are there some intermediate reactants? And what is a chemical mechanism? So it's a pure academic question. What to find and describe kinetic mechanism? Another group of problems is industrial problems. Here, chemical mechanisms, sometimes known, sometimes unknown, sometimes not important. It is necessary to know what is, for example, what is degree of cure during the process at given time and temperature. What is degree of sintering? What is degree of reaction for given temperature? It's the first part, it's called predictions. Another one, to find temperature profile if we know the result, just to optimize industrial processes. If we speak about degradation, the question, what kind of data could be used to answer all our questions? During the degradation, the products of degradation or decomposition are gaseous and they go away and the mass will decrease. So we just take our sample, make heating and measure a mass. And at the beginning, mass is high. At the end, mass is low. And somewhere we have a degradation process, like a change of this mass. And this method called thermogrammetry. If we need to make kinetic analysis, then it's not enough to have one curve. We must have a slow heating, fast heating, and have a different curves of mass loss for different conditions. If we speak about differential, if we speak about curing reaction, then the mass is the same. But we must measure this process and we can measure the energy of reaction because some reactions are exothermic and we can measure the heat flow, the heat which will be produced during the chemical reaction. We just this method called differential scanning calorimetry. We take two crucibles, one of them has sample, and we make heating. And if reaction is exothermal, then we have a peak. For kinetic analysis, we need several measurements. One is slow, one is fast. If we speak about materials which are firstly liquid, then elastic, then maybe in glass state, then we use rheometry. It's very interesting. In this case, we take our rotational rheometer, put a sample, make heating, and then we have dependence viscosity on the temperature during the curing reaction. Firstly, during heating, viscosity goes down because material will be more liquid without any chemical reaction. Then it goes up because of chemical reaction and material will be not goes from liquid to elastic state or maybe to glassy state. And then if the curing is finished, the curve goes down because material will be liquid for higher temperature without any chemical reaction. Usually we need several measurements with slow heating, medium heating, fast heating, and then we can make analysis. If we speak about ceramics, then we measure length length change, because during the sintering there is some shrinkage of materials up to 30%. And during the heating of material, we have thermal expansion of initial material, thermal expansion of the product, and some shrinkage during the process. If we make several measurements at different heating rates, then we have several curves. Up to now, it does not important. Up to now, we have completely different signals, and we must make some analysis of this. Second part shows how to make analysis of these materials. Firstly, if we speak about different signals, we must recalculate different signals to the same value, which shows chemical reaction only, which is independent what kind of signal it was. Was it mass or DSC, or maybe heat flow, or maybe length? For example, with mass, we have initial mass, final mass, some current mass in our point, and if we make a ratio between the current mass loss to the total mass loss, then we have some value which called alpha. It's called degree of conversion, extent of conversion, or extent of reaction. Sometimes it's called reaction progress. This value is 0 if reaction still not started, and it is equal to 1 if reaction is already finished. And this value shows us how reaction goes on from 0 to 1. If we speak about DSC, about heat flow during exothermal reaction, then we make a ratio between the partial heat flow, here, the blue one, to the total heat flow. So partial enthalpy to the total enthalpy, and we have again a value from 0 to 1, which is called conversion. If we speak about length, about shrinkage, about ceramics, then we have a thermal expansion baseline for a reactant before our process. We have a baseline of thermal expansion for product after our process. We have some intermediate value for current state, and make a ratio between the current length change to the total length change, and again have a value of conversion which is changed from 0 to 1, and show how reaction goes on. If we speak about viscosity, it's really very interesting. Viscosity of initial material shows a baseline depending on temperature. If we speak about the heating, then it goes down. For the product, we have a baseline which shows viscosity of product, which goes down with heating. And we have a changing between this baseline during our chemical reaction. Again, we have a ratio between the current viscosity change to the total viscosity change, and have a value from 0 to 1. So it doesn't matter what is the original signal. Is it TGA or DSC or viscosity or dilatometry? For each case, we recalculate measured data to degree of conversion. And now we can make analysis for degree of conversion. How it works. First step of all process. Firstly, we have a measurement of raw data. For example, DSC or TG or dilatometry or areometry, it doesn't matter. Then we put this data in our Kinetics Neo software and recalculate all this data to degree of conversion. We subtract baseline and have degree of conversion. Now we have several curves, which this curve has different shape depending on time and temperature. The shape is different, but what is the same? The same is the chemistry of this process. The same is initial substance, the same is product, the same is chemical reaction or chemical equation, what material goes to which material. The same is the order of reaction, the same is the activation energy. So there are some parameters which are independent on time and temperature, and they are the same for all these measured curves. So we can extract these kinetic parameters from the set of measured curves. We can use different approaches. First, it could be model-based approach or model-free approach. And if we have this set of parameters, which is independent on time and temperature, then we can use this set of parameters for predictions. For example, predictions for isothermal predictions for several years. What is the lifetime of our material? Maybe dynamic predictions, predictions of degree of cure or viscosity. We can make optimization of the temperature profile for industrial process. And now about kinetic modeling. Really, we speak about some process where a reactant goes to product. A reactant has some value of energy, product has some another value of energy, and reactant goes to product over transitional state, and this transitional state has additional value of energy. So if the molecule of reactant has this additional energy, then it goes to reaction and goes to product. If it has no this additional energy, then it doesn't react. This energy called activation energy, and if we have higher temperature, then more molecules has this activation energy and more molecules react, and reaction rate will be higher with high temperature. Generally, it was described in last century. No, it was almost more than 100 years ago by Arrhenius. We have a reaction rate where alpha is our degree of conversion, activation energy is E, A is pre-exponential factor, means collision frequency, and F of A is our reaction type, maybe nth order reaction or autocatalytical reaction, nucleation reaction. This is a main equation, but this main equation practically could be applied by two other ways, by two other approaches. First of them called model-free approach. It is very simple, very easy. It was created in last century, and here only reactant and product exist. No any information about intermediate steps or intermediate product taken into account. And for this general approach, only one chemical equation exists. Only one Arrhenius equation exists. And that's all. But you know, in reality, it's not so easy. And sometimes at the beginning of reaction, activation energy has one value. At the end of reaction, activation energy has another value. So process is more complex than just A goes to B. And in this model-free approach, it was assumed that the value of activation energy depends on conversion. So at the beginning, it could be one value. At the end of reaction, it could be another value. The same with pre-exponential factor. Main assumption of model-free analysis, only one equation. Activation energy pre-exponential factor depends on conversion. Reaction rate at the same conversion is only a function of temperature, and total effect is always the same for all curves. Changes of mechanism should be done at the same conversion value. That was a simple model-free approach, which could be calculated usually in Excel or maybe on the paper. Another one is model-based. Here we speak about a real individual chemical reaction which happens during the complex process. We have intermediate reactants and we have intermediate steps. And if we have the first step, A goes to B with some concentration A and B, then we have a first chemical reaction for this step. It has their own activation energy, their own pre-exponential factor, and their own type of reaction depending on the current concentration. If there is a second intermediate individual reaction step, then there is a second chemical reaction with the own activation energy, own pre-exponential factor, and the own reaction type. The assumption for model-based analysis is that the total reaction consists of several individual reaction steps, and each of them has own chemical reaction or kinetic reaction, but all parameters like activation energy or pre-exponential factors are constant. We have one value for the first step and another value for the second step, but it is always constant. When model-free analysis works. So model-free analysis is sometimes very easy. Sometimes it works only for 1 point and you can just calculate it on the paper. For example, you can take maximum point. Here we have measurements with different heating rates. You put this point on the Arrhenius graph, where x-axis is 1 divided by absolute temperature, and vertical could be different, for example, log on heating rate or on reaction rate. If we make a same with different maximum points from different measurements, from different heating rates, then we have a straight line. And from the angle of a straight line, the activation energy could be found. A result of 1 point model-free analysis is only one value. What happens at the end doesn't matter. It was not analyzed at all. A second group of model-free methods are multi-point model-free methods. Here, the same is done not only for 1 point, but for several points. For example, we can take point with alpha or 0.5, where a half of reaction happens, just to take points from different curves, have a straight line on Arrhenius plot, have the angle and activation energy for this value of conversion. Then we can take another value of conversion, another points, another straight line, and we have another value of activation energy for another value of conversion. Generally, we can do the same for each value of conversion. Conversion is the value from 0 to 1 during our reaction. And as a result of multi-point model-free method, we can find a function where activation energy is a function of conversion, function of alpha. Main rules when model-free method is applicable. First, a total effect must be the same for all measurements. Let's see the first picture. Here, the end mass is always the same. Can model-based, model-free method be applied? Yes, it could be applied. Second picture. Here, result is always different. Can model-free be applied? No. What to do to apply model-based method with competitive steps? Second rule, the reaction must have peak always on the same direction. First picture, the peaks have the same direction. Can we apply model-free method? Yes, we can. Second picture, the peaks have different direction. Can we apply model-free method? No, we can't. What to do? We should use model-based method and have a first step for positive peak and another step for negative peak. Second rule, model-free method can be applied if the mechanism changed at the same conversion, like here. First picture, here we have changes of mechanism always at the same conversion. Can we apply model-free? Yes, we can. Second picture, mechanism change at different conversion. Can we apply model-free? No, we can't. What to do? We should use model-based method with comparative steps. Mechanism could be changed several times, like here, but if it happens at the same conversion value for all curves, then model-free can be applied, like here. First picture, yes, model-free can be applied. Another picture, curing with diffusion control. Here we have different the changes of mechanism because of diffusion control happens at different value of conversion. Can we apply model 3? No, we can't. We should use model-based method with diffusion control. Advantages and disadvantages. If you speak about bicycle, it's easy to learn, it's easy to use, easy to ride. In Germany, we have normally the children which start to ride at 2 years old, if they're 2 years old. But if you have a long distance, then there is a problem. If you have a road with high hills, then it's a problem, and only the power of the body could be applied. Another way, just to use the car. The car has the engine and it is power. You don't think about your muscle body. In this case, it is work, has no problem with distance, has no problem with hills, but it requires learning. Usually, it is not very hard to learn the drive, but you must learn it. And if somebody drives the car the wrong direction and has accident, then it's not a problem of a car, but the problem of the driver. And if somebody has curve with 2 peaks and try to make 8 reaction steps for each and fails, then it's not a problem of the method, but the problem of the person. If you speak about model-free analysis, it's like a bike. It's very fast, it's one click, it's easy to learn, easy to use, but it doesn't work for mixtures, competitive steps. It doesn't work for curing with Kamal-Surrer reactions, with diffusion control, crystallization, with steps of different directions for highly overlapped steps. It doesn't work if a reaction mechanism depends on heating rate and it has no any information about intermediate steps and reactants. If we speak about model-based analysis, then it works for all this situation, but you need elementary chemical knowledge about the process. It's the first, and the second, you need to know the rules, how to apply this method. And the rules are in ICTAC kinetic recommendations. You can find it here, or you can find a link on our Kinetic website. Now we speak about unique features of Kinetics Neo software. Here we have a different for model-free and model-based curing and crystallization. Now I would like to speak only about unique features. If you would like to know what are the all features of Kinetics Neo, then you should go to kineticsnetch.com, then find technical data sheet. And here you have all features of Kinetics Neo software. Here we have 11 model-free methods. We have different model-based method predictions, some standard predictions or unique predictions, and optimization. For example, standard predictions are predictions for isothermal conditions, dynamic conditions, step iso, adiabatic, and climatic predictions, and so on. First unique feature, what is really important. Kinetics Neo software fulfills all ICTAC recommendations for kinetic analysis, except of distributed reactivity analysis. ICTAC is the International Confederation for Thermal Analysis and Calorimetry, and the NETZSCH was the only industrial company who was invited to develop these kinetic recommendations for multi-step analysis. Our software includes the following recommendations from these rules. They are model-free analysis, multi-step model fitting analysis, diffusion control, crystallization, Kamal modeling for curing, and deconvolution analysis, which contains some of peaks. Unique feature is a model-free method, which called numerical method. Right now, our software contains a lot of model-free methods. Mostly known of them are Ozawa method, Kissinger Akahira Sonoza, Friedman ISTM 2070, and Vizovkin method, which is sometimes called as model-free kinetics. They are common, they are well known, and they are inside our software. Additionally, we have numerical optimization. And numerical optimization is the method which finds the activation energy and pre-exponential factor from numerical optimization and the best numerical fit between experimental data and a simulated data. On this picture, we have a copper sulfate. Points are experiment, lines are simulation, and numerical optimization has a best result, a best fit to experiment. And each has a sum of deviation squares is only 2. Friedman has a little bit higher, Vizovkin a little bit higher, and all other methods are really high. That was a first unique feature. A second, model base. Unique feature of our software is just a possibility to create a model with different number of individual kinetic steps. Here we have no limitation of these models, and there is no limitations of the kinetic steps inside the models. So if it is necessary to have a model with 20 steps, no problem, the software allows you to do this. The steps could be connected by different possibilities. They could be independent, consecutive, or competitive. And it is only one click, just make additional step or remove step. It is only one click to optimize the parameter for one individual step, individual reaction step, or for whole model. And each step has their own type of reaction. The well-known of them is a reaction of nth order, but it is very simple and it is used not so often. Usually there could be some reactions without a catalysis or maybe nucleation according to Avrami, sometimes diffusion reactions or phase boundary reactions. The unique feature is Kamal-Surur equation. It is special for curing, and this exists only in our software. Additionally, we have for curing a reaction with diffusion control, where we take into account dependence on the glass transition position. And here we use Di Benedetto model or splines for dependence of glass transition temperature versus conversion. The last unique feature or last unique model is a Nakamura equation for crystallization process. It is very important for thermoplasts. Curing. If we speak about curing, then we have a general Arrhenius equation, but this Arrhenius equation usually cannot describe curing. Why? Because the curing process, according to the chemistry, has two parts, where a reactant goes to product by two different ways. A first way is nth order reaction, and a second way is autocatalytical reaction. These two ways have their own different activation energy, they have different pre-exponential factors, and autocatalysis has the part which shows the autocatalytical nature of this process. This equation has a lot of parameters, and the parameters could be found by software to have a best fit. And then you can make some kind of predictions. that was a really unique model for curing. A second unique model for curing take into account a glass transition. Usually we speak about material which could be a polymer, which could be either in glassy state or in rubber state. In glassy state, it has their own shape and could be broken. And in a rubbery or liquid state, or in a rubbery state, it is soft and it could not be broken. It could not have their own shape. If we speak about curing reaction, then in glassy state, reaction is slow. In rubbery state, reaction is fast. And the point between these two states is the glass transition. The problem is that during the curing reaction, the glass transition has not the fixed position. It moves from low value to high value during the reaction. So, and if a glass transition has some moving, then we should calculate if our sample temperature below glass transition or above glass transition, if the curing slow or fast. Here we have measurements with different heating rates from 0.2 K per minute up to 5 K per minute. The points are experimental data, and a solid lights, you see here a little bit difference, are our simulation. Here at the beginning, material is liquid. We have, for example, coating or paint or adhesives, and here reaction is fast. Then we have some point where sample temperature is equal to glass transition. Here we have vitrification, and material goes to glassy state. And after that, the curing goes very, very slow because we have material in glassy state. So we have change of the mechanism of curing reaction. And this changing of mechanism happens at different points. Here, let's take a glue and wait at constant temperature. The curing reaction here happens, and yeah, we're just waiting. At the beginning, material is liquid and the curing is fast. And at the end, material is not liquid anymore. It is in glassy state, and reaction is very, very slow. The point where we have a changing of mechanism called vitrification point, and we can find this vitrification point for different isothermal conditions. Finally, we have so-called vitrification line, and this vitrification line shows what is the state of material at different temperature. If you make the isothermal curing for the same material for 160 degrees C, then we see that where the material change the state to the glassy state. And we can do the same at low temperature and see that it happens, yeah, at very, very long time. Here we can find or just see what is the degree of conversion for different temperature. So this picture called time temperature transition diagram. Here we have a time temperature transition diagram for curing. This time temperature transition diagram shows the state of material, is it glass, liquid, or rubber, for isothermal conditions with no temperature and time. After vitrification line, material is in glassy state. Before vitrification line, it will be either viscous liquid or rubber, depending on the position on gelation line. This is time temperature transition diagram. It could be calculated or simulated in the software with one click. And if you have no software, you must make isothermal measurements during several months just to get this all information. And here is really unique for the software. A second unique feature, or last unique feature for curing, is our rheological data. Now we take some adhesive, just two-component adhesive, put it into a rheometer, make heating, and see what is the viscosity of this adhesive during the heating. There are two measurements, two experimental measurements. A first one is the heating, has a heating with 2K per minute, and then isothermal. This is a temperature curve. A second one has a 5 Kelvin per minute, and then isothermal, again temperature curve. And here in the top part of this picture, we have two curves, which are experimental curves, which shows viscosity, measured viscosity. We see here that there are two steps, a first exothermal step, the first curing step, and then the second curing step. Here we can apply model-based analysis, which contains two steps. The last picture shows conversion over temperature for experimental data. If we remove from experimental data the baseline, then we have conversion. And here we apply two-step reaction. The points are the experimental data, and the line is our simulation. You see here a little bit difference. But generally, we have very good fit, and we can say that this model-based or this model from model-based method can describe our measured rheological data. If we apply the same model for viscosity, then again we see that there is very good fit because the points, the experimental data, and the lines which are simulated data with this two-point model. But this model is not a target. It's only the mean to predict reactive behavior and viscosity of material at the new conditions. For example, if you want to know what is degree of curing for the following temperature program: isotherm, heating, isotherm, and cooling, then we can put this temperature program into the software, use our existing two-step model, and calculate degree of conversion. Now we see the first step of the curing and the second step of the curing. Again, we can use a simulation not only for conversion, but for viscosity. The software is able to predict viscosity for the same temperature program or for any temperature program. You can put here any temperature program and make predictions. Again, here we have isotherm. During isotherm, viscosity goes up because of the first step of curing. During the heating segment, firstly, viscosity goes down because it's normal behavior of viscosity with temperature without any chemical reaction. Then it goes up because of curing. And then during isotherm, we have the end of a second step of curing. During the cooling, the viscosity goes up as it should be without any chemical reaction. A next unique feature of Kinetics Neo software is not connected with curing, it is connected with crystallization. Crystallization is very important for users who work with thermoplasts and requires fast cooling. For example, during production of plastic PET bottles. Do you like transparent plastic bottles or not transparent? So do you want to see what's inside or not? If you want to see it transparent, then we can find or simulate conditions where crystallization doesn't happen and material stays amorphous. Here we have a general chemical general kinetic equations where degree of conversion change has dependence on pre-exponential factor, reaction type, and some dependence on temperature. Here, reaction type is just standard Avrami nucleation, which is standard for any crystallization process, and dependence on temperature is not Arrhenius anymore. Now we have dependence of temperature, which according to Hofmann-Lauritsen theory, and it depends on the melting point, and depends on supercooling. The higher supercooling, the faster crystallization, and it depends on the glass transition here. Because below glass transition, material stays in glassy state, and it is amorphous, and there is no crystallization happens in glassy state. Example, we take PT, make cooling for different cooling rate, have several cores, and make one-step kinetic equation, one-step kinetic model according to our Nakamura crystallization kinetics. And now we would like to know what happens if the cooling will be a different cooling rate. What is the degree of crystallinity? We can make predictions of conversion during different cooling rates or during different isotherms, it doesn't matter. And we see that for very, very, very low cooling, crystallization has a high conversion rate, and it means that degree of crystallinity is high and material is not transparent. But if the cooling is very fast, then a final conversion is low, and there is no crystallization happens, and material stays amorphous and transparent. And now you know that if you would like to make a transparent plastic, then you must make very, very fast cooling. Last unique feature, its model-based method can show reaction steps and concentrations. Let's see here. We have two steps. We have experiments with two peaks, and therefore we use two-step model. For two-step model, we have a possibility to show a first step as a first peak. Here you see it is individual, and we can show another peak. In this case, if you have several peaks, then you can show each intermediate step as each individual peak, and you can see where this peak is placed. And again, you can see here the concentration of each reactant, initial material, intermediate material, and final product. For two-step kinetic models with different directions, we have again two-step model. We can see a first peak is negative, second peak is positive, and we have some intermediate material, intermediate reactant, which has a concentration 0 at the beginning and has a concentration 0 at the end of reaction, but non-zero concentration somewhere in the middle. Very small feature is a Bézier baseline. If you have some background process, then it's very easy, or it's very important to have correct baseline. Here, for example, linear baseline has wrong slope at the beginning and at the end. The sigmoidal baseline has some things in the middle which does not belong to background process. Tangential baseline has also something which does not belong to background process. In this case, we use Bézier baseline, and Bézier baseline has very, very nice curvature, which is responsible which shows our background process, and now we can subtract it and make analysis very well. It is used if we have some background process or if baseline is still unstable, for example, at the beginning of segments. Software can export equations and then use it in FEM software for complex geometry of your volume, big volume. You can calculate temperature distributions and concentration distributions. We have our website, kinetics.NETZSCH.com. We have a training course with different examples. Here we have step-by-step instructions how to solve standard cases. Here, for example, we have a demo version for 30 days, and our kinetic software contains standard features. Firstly, contains standard features. Then it contains unique features like very powerful model-based analysis, special curing and crystallization, and hope it will help to our existing and new customers. And we have special academic version for university with very attractive price. So I think that was enough, and we can just speak about your questions.
Okay, thank you, Dr. Moukhina, for this exciting presentation. In the meantime, we have already received some questions, and you are still able to send some questions to us. The first question that came up was, does model-free method assume only a first order reaction?
No. Model-free method is the method without any assumption. So here the calculation of activation energy is done without any assumption at all. Therefore, it's called model-free method because there is no any model at all. It is for calculation of activation energy. And for activation of pre-exponential factor, it is necessary to have some assumption of reaction type. This is a second part, and this is really does not really belong to model-free method. And for calculation of pre-exponential factor, it is necessary to make some assumption, and this assumption could be first order reaction, or it could be something different. In our software, we make assumption about the first order reaction in order to calculate pre-exponential factor in model-free analysis.
Okay, thank you. Another question that came up was, how many rheology runs are enough to plot TTT graph?
So now we still have a TTT diagram only for DSC data, and for DSC data it was about 5. But for rheology, we still have no TTT diagrams. We did only normal kinetic analysis, but without TTT diagram up to now.
Okay.
Yeah, but we plan to do this.
Okay, and another question. Can you use the software for other thermal instrument vendor data files?
Yes, we can. So you need your data as a text file or ASCII file containing 3 columns: time, temperature, and signal. And if this file contains 3 columns, then you can import it in Kinetics Neo. And it doesn't matter what is the origin of this file. Is it NETZSCH instrument or some another instrument?
Okay.
In any case, you can just go to our website and there is some step-by-step instruction how to load non-NETZSCH data.
And one person asked us, have you done any modeling and predictions on formaldehyde-based thermosets resins cure? And if so, if we can share the data.
What kind of thermosets?
A resin cure.
Yes, we did.
Okay. So maybe we can send it out to this particular person.
Yes, we have some notes, application notes, and I think we can send it.
Okay. And another question, if it's okay with you.
Yes.
DSC data, if you have melting and vaporization 2 steps, can you use the data for kinetics study?
If we speak about melting of polymer, then if you speak about melting of metals, then no, it doesn't work. If you speak about melting of polymer, then we have a really moving of the peak with the higher heating rates, and then we can describe this peak with a normal kinetic equations. So we can apply it. And for evaporation, normally the Kinetic software was created for chemical reactions, but occasionally it was applied for evaporation too. So I have a data where we have evaporation peak and Kineitics Neo software work for this peak.
Okay. And I would have 2 other questions, if it's fine with you.
Yes.
Could you introduce more about the Avrami equation application in the Neo from the point of nucleation?
So right now we have what do you mean? What does it mean more? Right now we have Avrami of the second order. It means the 2-dimensional Avrami, 3-dimensional Avrami, and nth dimensional Avrami, where n is unknown value of dimension. And here the software can find the value of n just to make a better fit. And what does it mean more? I really do not understand. Yeah,
So,
probably I will write. Yes.
Okay, so we will write to them. And the last question, what can I do if I want to analyze a crystallization of a substance that is no polymer and has no glassy state? In this case, I suppose I can use the Nakamura equation.
Yes. So in this case, you should put in this equation in, for example, Hofmann-Lauritsen. Nakamura has no information about dependence on temperature. So if you speak about isothermal crystallization, then it doesn't matter how it depends on temperature. You can just take normal Avrami, and that's all. And there is no dependence of temperature. And if you would like to make the crystallization during the cooling, then it is necessary to have some dependence of temperature. And I know 2 approaches. The first approach, just to try to apply Avrami approach, just to apply Arrhenius approach. And in this case, the formal value of activation energy will be negative because the lower temperature, the higher crystallization rate. This is a first point or first approach. And a second approach, what we have, it take into account the melting and the glass transition point. I could imagine that for materials without glass transition, you can just put nominal glass transition at very, very, very low value. And then it will be this existing Hofmann-Lauritsen theory will depend only on supercooling. And that's all. So the higher supercooling, the faster crystallization rate.
Okay, perfect. Thank you. We will end the webinar now, but all questions that we didn't answer, we will send out an answer to you via email, and you will also get an email with the recording of today's session. So if you're interested to watch it again, you can do so. Thank you all for your time, especially thanks to Dr. Elena Moukhina for this great presentation, and I wish all of you a nice evening or day, depending on where you live.
Yeah, thank you very much for the attention and for your time. Bye.
Goodbye.